So I'm going to give you another challenge problem. This is kind of it's actually a really good problem. This is actually a problem posed by Charles Dodgson, or Lewis Carroll of Alice in Wonderland, who was, if you didn't know, a maths tutor at Christ Church once upon a time. So the idea is I have a rope going around a pulley, frictionless pulley, and on one end of the rope I've got a mass, whatever, say it's 100 kilogram mass, pulled down by gravity. And on the other end of the rope, this is going to stretch my artistic abilities, but there's a monkey, and the monkey is 100 kilograms. So, okay. That's sort of... Okay. So this is a constrained system. There's a tension in the rope, which is connecting these two objects that are the exact same mass. All right, so then what Dodgson suggested is that the monkey starts to climb the rope. And then the question is, what happens? Okay. I'll let that just sit there, let you think about that. It is a non-trivial question, and it kind of depends on how exactly, what we mean by, how exactly the climbing is happening and so on. But yeah, let's leave that there. This is what we were doing last time. Pendulum, we were talking about constrained systems. Here's a pendulum on the end of a massless rod. We worked out Newton's second law has the radial form, which is a second order equation for theta, the angle with the vertical. And, oops, that's not a zero. That should be a t. The e theta version of the equation looked like this. T is the tension in the rod, right? The object is pulling on the rod, and the rod is pulling back with a tension T, which must be positive, otherwise it's not pulling. And what we said is that the point is I don't know T. So really you can view it as I solve the first equation for the motion theta, and once I know theta, then I can work out what the tension is at any given moment. Okay? So there's actually a lot more kind of nice calculations one can do with this system. So one calculation is we can look at equilibrium and stability, and this is kind of I guess obvious and intuitive. There are two equilibria, so theta e equals 0 and pi are both equilibrium points because the sign goes away, so I get forces theta dot dot equals 0. And I won't put all the details on the board because it's effectively a very standard exercise with the tools we developed about a week ago. If you do linear stability, so theta equals theta e plus some perturbed variable psi, what you find is that 0 is stable with a frequency of oscillation which is 2 pi, omega equals square root of g over L, which is quite almost immediate because I'm doing linear stability. That sine theta linearizes to a theta, and that's simple harmonic motion with a root g over L. That means that the period of oscillation, which we might call t, is just 2 pi over omega. So that's 2 pi root L on G. And that's the bottom. So that means if I give it a small oscillation from being happily sitting at the bottom, that's the amount of time it should take to do one cycle. Theta equals pi is also an equilibrium that's sitting at the very top, and it won't surprise you that that one is unstable. And if you do the calculation, you confirm that. So theta E equals pi is unstable. If I give it a little nudge from sitting right at the top, it doesn't come back, right? Okay. Let's talk about energy in this context. Find a better pen. So E 1/2 m we've argued last time that a constraint like that does not do any work, so it doesn't impact our energy. So we do have the kinetic energy plus potential energy is going to be a constant, and here V, the only potential energy is gravitational. So V, which is like the Z coordinate, which in that coordinate system, mgz, which is minus mgl cosine theta, the way we've oriented that. And R dot, as we worked out before, since the radius stays fixed, is L theta dot E theta. So therefore, conservation of energy looks like m over 2 L theta dot squared plus, it is minus mgl L cosine theta equals E constant. Since that's not changing, I can work out what the constant is by taking any time points. Most naturally, I set E from t equals 0. So E, whatever initial angle and theta dot I give at t equals 0, E is going to be m L squared theta dot of 0 squared over 2 minus mg L cosine theta 0, theta of 0. So one kind of thing we could do with that expression is think about the following thought experiment. So if I start at some angle, call it theta naught, and let's say what I want to do, I'm at the playground and I want to swing the swing all the way around. So how hard do I have to push? What theta dot of 0 do I need to give? Which is different, pushing to get this thing to swing all the way to the top. So question. Well, so if I'm going to reach that point, then of course this is the point corresponding to theta equals pi. And what do I need to be true? I need to have reached that point and still have theta dot non-zero, right? So the pendulum stops when theta dot equals 0. And what we need is the energy to be high enough so that I get all the way to theta equals pi when that happens, right? So if I put in theta equals pi, that's like the statement that minus mg theta stops, the pendulum stops when theta dot is 0, which is when mgl cosine theta equals E. So we require, I put in pi here, I need E to be at least mgl, right? So if E is greater than mgl, then our pendulum makes it all the way to the top and still has a little bit of energy. Yeah. In fact, if E is greater than mgl, I don't just make it to the top, I swing a little bit over the top. What happens next? So I've given this thing a big push, it's made it all the way to the top. Then what? Okay, you want to think it just keeps going, right? Given enough energy. A way to see that is think about like an energy landscape. So if I plot V of theta, V is just a minus cosine, right? So V is looking like that, and this maximum point is mgl. And I guess what I'm doing in the experiment is starting here, and if I just let go, this is our usual picture, ball rolling in a potential field, it's going to do that, but I'm starting here and giving it some velocity so that it gets past here. And we see that if my total energy is greater than mgl, then every time it gets up to here, it still has some theta dot 0, which means it's just going to continue flipping over and over because there's no energy being lost, right? So my total energy is sitting somewhere above there. Then this experiment where I started with some velocity is the same as the experiment where I'm up here with a little bit of velocity. And it's just going to keep doing this loop. Okay. When we do that calculation up there, the linear stability, we get a period, right, from the simple harmonic motion. But that's linear stability, which means that's an approximation. I've linearized the sign. What if I want to know the actual period? It's sort of the difference between an actual pendulum, which has the sine theta, and the sort of pendulum we think about that you've done, say, in A-level physics, which we've already linearized to simple harmonic motion. If I want to work out the actual period, I can. In other words, if I don't linearize, I keep the full theta dot dot plus the g over L sine theta. What period, how long does it take? I'm imagining I start somewhere without any velocity, so the pendulum is going back and forth in my potential field. How long does it take to get one cycle if I have the sine theta there? So we can let theta be theta 0. Let's take theta dot of 0 to be 0. Theta of 0. Theta 0, theta dot of 0, 0. So that means that our total energy in this system is just the minus mgl and the key, let's go all the way down. Okay, I don't know how to solve that equation, and it's second order. I'm a bit stuck looking at that equation. But this equation has time living into d theta dt, and we did this before generically. I can extract time by thinking about integrating that equation implicitly with theta and t. Right? So theta dot squared, if I plug in that value of E and solve this energy equation for theta dot, I get theta dot squared is 2E over ml squared and plus a 2G over L cosine theta. Right? That's d theta dt. So if I take a square root and divide, this is independent of t, so I can divide this whole thing below the d theta, and I end up with a dt sitting on its own, so that's a time, and I end up with an ugly integral. So think of that as d theta dt squared. Take a square root, put the dt on the right-hand side, and we get an expression t equals, okay, there's a plus or minus, which is really the time irreversibility of the system, plus or minus the integral was viewed as a indefinite integral for the moment of this rather ugly square root in the denominator, 2e over ml squared plus 2g Okay, that's not very nice. If I could just integrate that, then I would have an expression that tells me the time as a function of theta, and if I can invert that, I would get the total path theta of t. Right? If I'm just interested in computing the period, then I can integrate over a specific range of theta, which is theta, well, if I'm doing the period, let's go here. Starting here, it's going to there, it's going to come back. Notice that the period is, there's a symmetry there in the form of that energy potential. So theta minus theta naught is going to go to theta naught, and so on. So I could write the period as the integral from minus theta naught to theta naught, or from theta naught to minus theta naught. Oh, sorry, that's halfway, right? So theta naught to minus theta naught, and then it goes back to theta naught. So I can write the period as 2 times the integral from theta naught to minus theta naught of that monster. I want to write it again. Or I can use the symmetry even further, which is to say that because this thing is perfectly symmetric about theta equals 0, however long it takes me to get to 0, it's going to take me the same amount of time to get to theta naught. And you can argue on the symmetry of V and what theta dot is doing there. So that's the same as 4 times the integral of theta naught to 0, or 0 to theta naught, of this ugly integral, and the d theta there. Yeah, so let's just take that one step further so I can, my E has an MGL cosine theta naught, which is going to live here. Cancel out the M, and then you have an L over L squared, which means both of these terms have a G over L if I'm sitting inside a square root. So I can pull out the root L over G if I flip it. And actually that's not surprising because that's the same term there, right? My linear stability, the scaling of my linear stability I expect to work the same. What I expect to be different is that 2 pi came from the approximation. I want to get the sort of proper coefficient there. So if I pull out that root L over G, then I get 4 root L over G times the integral 0 theta naught of square root of 2 cosine theta naught, sorry, theta. I think it works better to flip that. 1/2. Okay. There's probably a nice trick to integrate that. I don't know. You can put it in a computer and get that number. Depends on the theta naught. I'm going to leave the calculation here. The observation, though, is that the units, this is dimensionless, right? This is just an angle. So the units of t are the same as the units of square root of L over G. Which is, as I said, what we expect to be consistent with the linear stability, and that is a time. If you work out a length over a length per time squared, square root is a time. And effectively that 4 times the integral sets the constant. Okay. Right, so I think we'll leave the pendulum problem there. So that's kind of, in a way, a nice simple constraint. I'm always fixing my radius and just letting the angle vary. As I said briefly the other day, and you'll play with this in a problem sheet, we have to be a little bit careful in this motion that t is staying the right sign, right? What happens if t flips sign? So I said t, the way I've set it up, t should be positive. That's the rod is pulling the object back towards the origin. If I solve this system and I find that t becomes negative, what would that indicate? It's pushing instead of pulling. And you can think if I'm on a swing at the playground, this is like, because it's not rigid. If it's no longer pulling, it's pushing me. That's like I'm pushing it and it's going the other way. So that's like the chain has become slack, which means that the model is probably not valid anymore. Right? Same as we said for the snowboarder, a flip in sign of the reaction force is the condition that you leave the surface. Right, speaking about that, let's do an example for motion on a surface. Or actually, I want not an example, but I want to do a sort of set up the generic system. And I guess we could do this for more generic force, but gravity is the natural one to think about. So I have some surface. I have my mass constrained to be sitting on that surface. And let's say gravity is pulling it down. Call that vector g down. Normal reaction force pointing that way. And I didn't say it, but I mean a frictionless or smooth surface. So there's no, again, no force in the plane of the surface. There's no loss of energy, no friction. So actually, let's just write it here. So a smooth surface implies that the constraint force N is normal to the surface. And the one way to express this condition that I need to keep track that n doesn't flip is that you can see it in the picture. At any given time, n should be pointing the opposite direction from gravity. Right? If n ever points in the direction with a dot product that's positive with gravity, then things have flipped and the surface is now grabbing instead of pushing. Right? So I must have n dot, just write it as vector g negative, otherwise and again, simple way to think of that intuitively is our particle is on top of the surface relative to gravity. Gravity is pulling the particle into the surface, and the surface is pushing back the other way. Right, so by construction, that's a two-dimensional motion. Which is to say that the surface is a two-dimensional space, and as long as my particle is living in that space, then it's 2D, though embedded in 3D, right? Okay, so depending on the surface, this can be quite messy to set up. It's a much more complicated constraint than our pendulum, but there's a class of surface for which the equations look much nicer, and that's a surface of revolution. So what we want to do is play with the equations in the case of a surface of revolution, and really the idea is to exploit the axial symmetry. To simplify. Okay. So let's draw a little picture. So I'm going to let the z-axis be my axis of revolution. So I'll put an x and a y like that. And I'm going to suppose that we have a curve. That's not very good. I want it to be a bit smoother at the bottom. Okay, so I take some curve, rotate it around the z-axis, that's going to define my surface. So, really x and y don't matter. It's just, if I'm looking at this from above, there's a radial symmetry. And so if I define the surface by rotating the curve, let's write it as z is some function, I'm going to call it capital H of r around the z-axis. So this, so take a distance r, or for instance, just go out in the y direction. And this is for a given radius h of r. Right, so that symmetry suggests I should exploit polar coordinates, really cylindrical coordinates for a surface of revolution. So let's see what Newton looks like in cylindrical coordinates. We haven't done it before, but cylindrical coordinates is just polar coordinates plus a z, right, which is Cartesian. So that's our position vector r would be r er plus z ez, where now we remind ourselves that that er looks the same as it did before, having a cosine theta sine theta in Cartesian plus an extra z component, which is 0. In Cartesian. So all I've done is add the z, but that's a fixed vector, ez always pointing up, which means when I start taking derivatives, I get the same pattern taking derivatives here. Er dot becomes e theta with a theta dot. E theta dot becomes er with a minus theta dot, and so on. And then the z just becomes z dot and z dot dot. So everything's very simple extension from polar coordinates, which means that I'll just write them both. So r dot is r dot er plus r theta dot e theta plus z dot ez. Acceleration r dot dot and I've used our trick where I combine the terms in the e theta to be a d dt, r squared theta dot. Right, so if I write down Newton's second law, I get m times that equals the forces. I'm not going to write that whole expression again. M r dot dot forces, so I have gravity, which we're orienting, I didn't say it, but let's have gravity in the z, so minus mgz, ez. And I have n. And n is my normal reaction, which I don't know. All I know is that it should be pointing away from gravity and normal to the surface. Right, so really the question is, what do I do with this, right? There are a couple of challenges, right? We want to kind of list the problems or the aspects of this that makes it hard to solve. One is I don't know n. And two, I have three variables, r, theta, and z, and they're all kind of tangled up. Well, at least the r's and the thetas are tangled up in this quite messy, very nonlinear expression. So it's a nonlinear equation for three variables, r of t, theta t z of t, but that doesn't feel quite right because it's a two-dimensional problem, right? So I shouldn't really have three distinct variables. They're linked, right? So part of our challenge is figuring out how do I get to a properly two-dimensional problem here. Okay, so this is sort of the challenges of the system, but let's start collecting some useful observations. So the keys, well, let's state things we know about n. So we know that n is orthogonal to the surface, but let me state that in a different way. R dot, the tangent, the velocity vector, is always in the surface, right? And whatever the motion is, the tangent vector points into the surface, and n is orthogonal to the surface, so I can write that as the statement that n dot r dot is 0. We'll think about how we might use that fact. I can say more about n for a surface of revolution, so this is always true. For a surface of revolution, I can make another statement about n, which is that it's going to have no component going around the surface. Right? In other words, just geometrically, the normal to a surface of revolution does not point in the circumferential direction at all. And so n, in this notation, we can say that n dot e theta is 0 by the symmetry of the surface. Okay, that's going to be quite useful. 3, I think in any time solving these problems, you want to always have it in your head that there's two kind of distinct approaches you can take. I can look at Newton's second equations and see how far I can get in solving them, or I can recast the problem into the energy domain, and maybe in the energy domain some nice tricks pop out like we've seen over here. As long as we have conservative system, no energy being lost, smooth surface, smooth constraint, I have an energy conservation going to apply. So energy conservation applies. In other words, 1/2 m r dot squared plus v of r is constant. And since I only have gravity as the only conservative force in the system, v is just mgz. And one more useful observation to make up front. This comes down to the dimensionality. So I say it can't possibly be actually 3 independent variables, r, theta, and z. So what can I use to reduce that space from 3 dimensions to 2 dimensions? That's right. At any given point, the mass is on the surface, and the surface is defined by revolving this curve, whatever I called it, z equals h of r, around the z-axis. Right? That means z and r are not independent, they're linked by that function h. Right? So z, we can write it this way, z of t equals h of r of t at all times that the particle is on the surface. And by the way, that's why it's better to think of revolving a curve h of r around the z-axis. Sometimes we construct surface of revolution by taking z equals h of y, for instance, and revolving around the axis, but that's arbitrary and it's really h of r. Get the same thing. Okay, so I have these 4 facts at my disposal. Let's play around. Maybe I want to leave this where we can see it and come over here. So one thing I can do is I can take Newton's second law, and I can either dot with r dot, which is a little bit messy, or this one is much easier, dot with e theta. So if I dot n2 with e theta, and use fact 2, looking at our nice form for the e theta component, we get the same kind of thing we've had before, which is the d dt of r squared theta dot is 0. So r squared theta dot is a constant, and let's call that constant little h, as we have before. When we saw this before, we understood that as a conservation of angular momentum, and indeed we can derive that in a similar way here. So if I think about the angular momentum about so angular momentum is r, so angular momentum about the origin, so L0, is r cross m r dot, right? And if I want the components, if I want to think about the rotation around the z-axis, I take the z component of that vector, so dot this thing with Ez. And let's just do that. So you get Ez dot r e r plus z e z cross m times r dot okay, a lot of terms in that cross product, but I can immediately discount most of them because I'm taking the Ez. So anything that has an Ez, I'm going to ignore, because when I dot with Ez, it's going to be 0. The only thing that survives is when I take the ER cross an E theta, because that's going to give me an EZ, which dots with an Ez. Yeah. So that's R m, so I get m r squared theta dot. Or, from what we've just worked out, that's m times h. In other words, we can say generically that if I have motion on a surface of revolution, angular momentum about the symmetry axis is conserved. In other words, it's got the symmetry axis. If I set it sort of spinning in that, around that axis, there's nothing, that energy of rotation around the axis is not disappearing anywhere. You can understand it that way. Okay, so that's going to become quite a useful statement. What next to do with this equation? So I've used this. I can try to use this. It's a bit, well, yeah. Okay, so I could take this equation and dot with ER and dot with EZ. The problem with doing that is I'm going to have these unknown components of n, the ER and the EZ components of n, sort of two components that I don't know. I have these two separate equations. I'm going to be a bit stuck. So what I'd rather use is perhaps that fact, n dot r dot. So how do I use n dot r dot equals 0? Well, I can just work out r dot. I mean, I have an expression for r dot, so I can take r dot Newton's second law, and I know the n bit goes away, but that's quite messy. Let me see if I can use this fact in a cleaner way by using the symmetry of the surface. So here's one approach. Let's think in the plane. That's r and that's z. And this is a curve z equals h of r. I can define, let's call it vector tau, as a tangent vector to the curve of revolution. So in my picture here, I'm going to define that as tau. So tau, just by that geometry there, is just the derivative h prime of r. That's in the z component, right? So that would be like er plus h prime of r ez. And actually, we can work out exactly what n is in that picture too, or at least the direction of n. I don't know its magnitude, but I know that n is pointing that way because the other component would be into the board, which is the e theta. I'm rotating this thing. So n is, think of this as just the vector 1 h prime in er, ez components. I flip the two and put a minus sign. So n is going to be some scalar n times minus h prime er plus ez. That vector dot that one is 0. Yeah. And I've chosen the sign so that it's pointing up in the ez, which is what I need so that that should be positive. Right, I don't necessarily want to use that. What I want to do is get rid of the n from Newton's second law because I don't know it and it's causing me trouble. So if I take Newton's second law and dot with this tau, then the n is going to go away. So n dot tau is 0. So let's dot n2 with tau. So that gives me so I'm going to take this thing and dot with tau. Tau is an ER and an H prime of R EZ. So I just get this guy, R double dot minus R theta dot squared. And then that goes away. Z dot dot, the EZ gets an H prime of R. So I get plus H prime of R Z dot dot equals, that goes away, and that just gives me the gravity dotted with that tau, which is a minus mg, becomes plus, sorry, minus mg H prime of R. Okay. That's a big, messy equation, but I'm getting quite close to something that's at least one variable. So, theta dot is still living in this equation, but on the other hand, r squared theta dot is a constant. So I can look at this as r squared theta dot squared divided by an r cubed. Right? So this is r squared theta dot squared divided by r cubed, which is h squared over r cubed, which means I've gotten rid of the theta, and that h I work out from whatever my initial conditions are. I've still got r's and z's, but as we've said, r and z are not really independent. They're connected via the definition of the surface. So one thing I could do is get rid of the z's. So z of t, here, single ODE for r of t, I can use z is h of r of t, which means if I take a z dot, I get h prime r dot, and I can go further, z dot dot gives me an h double prime r dot squared plus an h prime r dot dot. Right, so in principle, I plug that into the z dot dot. I get rid of the theta in terms of the h, and now I have one second order ODE for r. And you give me whatever initial conditions. Principle, I solve that, and I've got the motion. Right. The problem with that calculation is that it's very, very messy. Right? That's a very ugly. It's got an r cubed in the denominator. It's got all sorts of nonlinearities, r dot squared, and so on. So possible to do that way. You probably have to do it numerically. We will pick up on Thursday with the energy approach and see if we can make a better progress. Let's stop there. Okay, shall we get going? So we've been looking at constrained motion, and we've kind of worked through some of the equations of a particle on a surface of revolution. Let's do an example. So I want to imagine the surface is z equals r squared over 2a. So this is like a bowl, parabolic shaped bowl, a some constant. And let's, a particle is projected horizontally from z equals with speed v. So I've got a marble in a bowl, and at time 0, the marble is at height z, and I give it a little horizontal push with speed v. And the question, different questions we might ask, but the question I want to answer is, does the marble ever make it to the bottom of the bowl? Okay. Of course, we expect yes, if I'm doing this with a real marble, but real marbles are subject to drag. Right? This marble is living in a vacuum with no air resistance. So it's not necessarily obvious that it should ever make it to the bottom of the bowl. Okay, so I'm not going to go through every equation, and for the most part, we've already worked out the equations last time. We just have a particular form of surface here. Last time we were doing Newton's equation, and we were doing some tricks to get rid of the normal reaction, and we ended up with this second order equation, which was quite ugly. And I said another way we could go about that is to think about conservation of energy. And conservation of energy, which is just going to, of course, say 1/2 magnitude of r dot squared plus potential energy is just gravitational, which is mgz, is a constant E. We can work out that E from thinking about the initial conditions. So our initial conditions, we have to make sense of this. So we're told that z equals A, so z of 0 is A. Projected horizontally, what does that mean with speed v? I need to turn that into an initial condition. So if we think R is RER plus ZEZ, right? R dot ER plus R theta dot EZ plus Z dot EZ. Sorry, this is an E theta. Yeah? What does it mean projected horizontally? We're saying something about this vector, right? Which is the horizontal direction? Theta, yeah? So that statement, projected horizontally with speed v, means the vector at t equals 0 is only in the theta direction and its magnitude is v. Right? So at t equals 0, r dot of 0 must be just r of 0 theta dot of 0 E theta, and that must have magnitude of v, right? Okay. Well, so my surface is z equals r squared over 2a, and z is starting at a, so if z is a, r is 2a, right? So r of 0 is 2a, and r of 0 times theta dot of 0 is v, right? Now actually what we need to use is the fact that we have a conservation of angular momentum about the z, right? This is the statement that r squared theta dot is h. This is what we derived last time from thinking about the theta component of Newton's second law. Question? Okay. Where's this coming from? So if I put z equals a and solve for r squared over 2a squared over, 4a, you're right, this was wrong. The mistake is up here. I want the surface to be 4a. Thank you. That should work. Yeah. Good now? So we're going to need to use this h, and effectively what I can do is I can work out what the value of h is, because I know that at t equals 0, r of 0 theta dot of 0 is v, and r of 0 is 2a. So therefore, this h is r of 0, which is 2a, times r of 0 theta dot of 0, which is v. So h is 2av. Okay. So therefore, my conservation of energy, r dot squared is, sorry, and I'm missing an m in here. The m is not going to matter because the m is also going to show up in the e and can cancel out of everything, but it should be there. Yeah, so I end up with 1/2 r dot squared plus r theta dot squared. But sorry, I want to write. So this is my, take the square of each of those components, sum of the squares of those components for kinetic energy, and this r squared theta dot squared I want to write as an h squared divided by r squared. And then I get a z dot squared plus, okay, we'll keep the m, plus mg z equals E. And the E, I can just put in the values of these components at at t equals 0. And at t equals 0, r dot is 0, z dot is 0. And I'm just left with the h squared over r squared plus mgz. So that's m over 2 times h squared, which is 4a squared v squared over r squared, which is 4a squared plus mga. So E, our constant total energy, is, what are we left with? The a squareds, the 4 go away. There's an m times v squared over 2 plus ga. I still have r's and z's, and as we said before, really they're linked to each other by the fact that they're stuck. It's on the surface, and the surface has a relationship between r and z. So I can eliminate r or z. So let's eliminate r in this case because I want to think about going the value of z. So to eliminate r, I just need to think about this relationship, which looks a little weird. So I'm going to solve for r from that z equals r squared over 4a. So r is 4az to the 1/2, which means that r dot, take a d dt, we get a 1/2 z to the minus 1/2, so that becomes a 2 root a z dot over 2 root z, I think. I'm pulling out the root 4a and taking 1/2 z to the minus 1/2. And right, so I can plug that in there. And now I have a single equation for z. And on the one hand, the benefit of conservation of energy is that this is a first order equation, right? It's just z dot. Effectively, if you're working with energy, you've already integrated once. So I don't have second derivatives, but it's quite messy. I could try to solve this equation for z dot. It's a z dot squared, and then I could try to separate and integrate. It's possible. It's messy. Actually, there's a little trick we can use to answer our question, which isn't going to be fully resolving the trajectory, but it'll answer our question. So I take this, I shove it in there, and I'm going to shuffle things around where I get a coefficients of the z dot. And after a little bit of algebra, you can write this as 1/2 1 plus a over z, z dot squared, plus a v squared over 2z plus gz equals v squared over 2 plus g over a. Sorry, g times a. So all I've done is I've factored out the things that have a z dot squared. These are the terms that involve z. And then this is the constant e. And I've gotten rid of the m. Okay. Now, this is still, as I said, this is quite hard to solve exactly. But my question was, does the marble reach the bottom of the bowl? And this equation looks a bit like T plus V equals constant. It's of course, it's come from kinetic energy plus potential energy equals constant. And I've shuffled things around a bit. So if I call this thing, I'm going to call it sort of curly T, because it's not quite kinetic energy. It's kinetic energy where I move one of the terms away. And this thing is not quite potential energy, but it's close. It sort of looks like P, a V. So let's call that curly V. And then this is like our E. In fact, that is just the E. And the key is that, so this has that kind of form where the T has like kinetic energy z dot squared plus this kind of weird factor. But nevertheless, this thing is positive or non-negative. And this looks like a potential field. And so I can think about the shape of this and make some progress on what's allowed to happen with z. In fact, you can already see that there's something funny happening. If z really did go to the bottom of the bowl, z goes to 0, there's singularities, right? So this already suggests that that probably can't happen. So if I plot v of z, so that's a function that's diverging at 0, and then as I go away in z, it looks linear. So it's doing something like this. And if you do some calculus, you can work out that that point right there, where v prime is 0, has solution z equals root a v squared over 2g. Now, as I said, this is not exactly kinetic energy plus potential energy equals constant, but it has the same kind of mathematical flavor. And we can really argue the same kind of statements about the trajectory. So what we're doing in our experiment is we're starting at z equals a. Let's suppose that's z equals a. With t equals 0, right? So at t equals 0, E is v of a, and t of a is 0. So it's very much like starting a ball rolling in a potential field that has that shape. And in fact, all of the arguments we've used before work the same way. The ball is going to start moving this way. It's going to be trading v. V is going to be going down, t is going to be going up until it comes up to this point. And at that point, E is back to v, which means t kinetic energy, or our sort of pseudo-kinetic energy, goes back to 0. So at this point, v is E, which implies t is 0, which means it stops, and then it goes back down again. Okay. So indeed, the particle can't reach 0, partly because there's a singularity there, but even if it weren't a singularity, this graph just isn't going to get to 0. And we can even go further. So you can do more calculus. You can say, I can work out what that point is, and that's the other place where, let's call that z star. Z star is such that all the energy is in the V. Right? So I set V equals E, solve for Z. One of those solutions is Z equals A, that's by construction. And the other solution, if you do a little bit of algebra on that, you get Z star is V squared over 2G. In my picture, I've drawn Z equals A to the right of this point. Doesn't have to be that way. But basically, there are two scenarios. If A is less than this value, then that means I started over here, and that means, in fact, it's kind of interesting, two experiments. If A is less than, what do we want to call this guy? Let's call this guy, well, I don't know, let's leave it like that. So two scenarios. If A is less than that value, root A V squared over 2G, then that means that the particle is always rolling to the right of A, which means that Z is going to stay between A and V squared over 2G. And if A is greater than that value, AV squared over 2G, then Z stays between you can see this is the same thing as A less than or greater than V squared over 2G. So the interesting thing about the experiment, one, the particle never makes it to the bottom of the bowl, and that's partly because the normal reaction force, as you get lower, you're doing these smaller circles, the normal reaction force is pointing more up and it pushes you back up the bowl. Basically, it's always going down, and then it comes back up, and then it goes back down, then it comes back up. In this scenario, in fact, you can really think of this as a statement on how hard I pushed. If I give it enough velocity initially, it never goes down at all. Right? I give it a horizontal push, it goes up the bowl, then it comes back down, then it goes up the bowl, then it comes back down. Which is quite, I think, an unexpected result. Okay. Want to move to our next topic, unless there are any questions on what we've done there. So what we want to do, this is part 6 of the course. Is to connect Newton's second law to Newton's law of gravitation, or more generally, inverse square law. So Newton's law of gravitation I have, let's put an origin here. I'm going to put a mass, I'll call it mass 1 there at position vector r1, and another mass here, called mass 2 at position vector r2. The law of gravitation says that the force, the gravitational force of point mass m1 located at position vector r1 due to, gravitational force on point mass m1 due to point mass m2 at r2. Let's write it this way, is F21, no, F, F1, 2, the force on 1 due to 2 is constant called Gn, product of the masses m1, m2, divided by the distance between them squared. It's the inverse square part of the law, so that's magnitude of, I take the vector r1 minus r2, magnitude squared, that's the distance between them squared, and that vector is going to point towards r2. So this is the vector r2 minus r1. And I need to make that a unit vector since I've already taken care of the magnitude here. So of course we can bring that together, and this is the same as r2 minus r1 minus r2. So I can write it as r2 minus 1 over the magnitude cubed, but it's a bit nicer to write it this way because it reminds us that really the magnitude of the force goes with the square of the distance between them, and this is just needed to make it a unit vector. Right, so that G is sort of, as we understand it, a universal constant. So that's approximately, has a very specific value, 6.67 times 10 to the minus 11 newtons, meters squared, kilograms to the minus 2. That is the gravitational constant. Same constant will apply for the attraction between Jupiter and the Sun as for any other matter in the universe, at least within Newtonian gravity. So a few notes. By Newton's third law, this is now the easiest expression of Newton's third law, the force on particle 2 due to particle 1 is the exact same thing, just flipped around. So F21 is minus F12. 2, gravity, as we know it, is always attractive. Particles, the masses are being attracted to each other, not repelled. 3, this is more of an approximation that's very useful. Let's consider the case where mass 2 is much greater than mass 1. So mass 2 is the Sun and mass 1 is the Earth. The claim, or the statement, is that particle 2 is approximately stationary. And at first that might seem a bit curious because we've just said they have the same force acting on each of them, just flipped around. But then the key is that if you think about Newton's second law on particle 2, that says m2 r2 dot dot equals F21. Because there's m2 over here, cancels out the m2 in the force, which means that the acceleration of particle 2 is only seeing m1 over here. Whereas, so if I cancel out the m1s and m2 is very big, acceleration of particle 1 is much higher than the acceleration of particle 2. So to a very good approximation, though it is an approximation. So actually the Sun and the Earth, if we had nothing else in our solar system, the Sun is not sitting stationary. It is also moving based on the gravity of the Earth, but it's much, much, much smaller than the motion of the Earth. So it's mathematically, we can effectively treat particle 2 as being stationary, and then the nice thing to do is take that to be the origin to work out the path of particle 1. Right, so m2 cancels, and r2 dot dot, say close to 0 if it just has the m1 there. So what we can do in that case is we can set r2, as I say, to be the origin, and then I can relabel. I don't need the subscript now, I just have r1, so let's just call its position vector r, and let's define m, capital M to be m2, and I'll use little m for m1. And then we can write that little m r dot dot is minus KER over R squared, where K is M G. So particle 1, which I'm labeling R, its force is in the radial direction, has an inverse square, 1 over R squared, and the constant has the product of the two masses and the gravitational constant. And this is the equation we want to make some sense of, but this fits into what we've been thinking about because that's a central force, right? And it just has this very particular form of the 1 over R squared. And then make a note, this has potential V of R is the antiderivative of the K over R squared, which is so it's a minus the antiderivative of that, which is a minus K over R. Take the derivative of minus K over R, you get a positive K over R squared, the minus that gives me the force there. Okay, and all of these statements we've been making apply in the past few lectures. So energy is conserved in the system. It's a central force, so that means the motion is planar. And what we want to do is kind of work out the possible paths of particle 1. But first, let's do an aside, or a couple of asides. So one aside is to ask the question of what we've mentioned at the very beginning of the course is there's kind of these two different laws we might use for gravity. When do we use this F equals minus mg Ez versus F equals minus k ER over R squared? You said that's what we've been using for gravity. This is what I'm telling you is actually the accurate description of gravity, at least within Newtonian mechanics. And it's about scale. So if I draw a circle and call that the Earth, and then let's give that radius R, and here I am sitting up here, and I'm going to do a little experiment of dropping something. So I'm sitting here, and I call that EZ, and I do an experiment where I drop something from height h. When I drop the pen in the classroom, it's being attracted to the center of the Earth. So the actual gravitational law of pulling the pen down is this one, but the R is not the distance from the pen to the floor, it's the distance from the pen to the center of the Earth. And that's where the distinction comes in. So really R, little r is big R, the radius of the Earth plus whatever height I have there. And then, of course, if I'm doing an experiment anywhere near the surface of the Earth, h over r is a dimensionless number, which we might call epsilon, which is, of course, very small. Right? So then the claim is that I can get that law as an approximation of that one. So if you take mg over little r squared, so that's mg over big R squared times 1 plus epsilon squared to the minus 1. Right? I'm just factoring out, I'm writing that way and factoring out the R, so I get a epsilon squared to the minus 1. And now I can do a Taylor series of that epsilon squared, so that's approximately mg over R squared times 1 minus epsilon dot dot dot. And actually, if you take the mass of the Earth times the universal gravitational constant divided by the radius of the Earth squared and plug those all in, you get about 9.8 meters per second squared, which is the little g we use. Indeed, this little calculation also tells you if you wanted to go a bit further in your approximation, if you're, say, above the surface of the Earth by a substantial amount, but not, say, far enough to be in some sort of orbit, you can do this and see what the next term you need is. But that's the connection between those two formulations. Another comment, which is sort of an aside, we will primarily be thinking about gravity, but there are other laws that follow the same form, and in particular Coulomb's law. This is if I have 2 point charges. So this is in electrostatics or electromagnetism, Q1 and Q2. If I have 2 point charges Q1 and Q2 at rest, then there's a force between them which has the exact same sort of form. So F1, 2, the force on the first particle due to the second satisfies so you get another universal constant sitting out front, which is written as 1 over 4 pi epsilon naught. I'll define that epsilon naught in a moment. Product of the charges, Q1 over Q1 times Q2, divided by the distance between them. So again, we need the R1, right, the distance squared. And be careful if I get on the first R1 that epsilon naught is called the permittivity of free space. It's just, again, a universal constant. Where's the double T? The only difference between this law and the gravitational law is that Q can be positive or negative. So if the charge can be a positive or a negative charge, which means that if both charges, so if Q1, Q2 have the same sign, in other words, both charges are positive or negative, then F1, 2 I'm writing it that way. I think my notes have it written the wrong way, I think. So if they have the same sign, it should be repulsive, right? Else return. Have I written that right? So R1. Have I written that right? So if they have opposite signs, that's negative, which means that's pointing R2 minus R1, and R2 minus R1 is pointing that way, which is attractive. I think that's good. As I say, we won't really play with that, but the mathematics works the same, except that you can have, of course, this additional feature of attractive versus repulsive. What we really want to do, so our goal for the next couple of lectures, is to use some tools that we've developed already and build some new tools to understand planetary orbits, and in particular, what's called the Kepler problem. Oops, planetary. Okay. So, I'm going to imagine a large object here. Maybe it's the sun. And we'll put the origin there. And then we'll have a single particle, a mass. Might be a comet, might be a planet. It's the only other thing that's in our picture, sitting here at vector r with mass little m. This is a planet, a comet, etc. Of course, if it's a planet, then I know that it's orbiting the sun, and I want to say something about the properties of that orbit. If it's a comet, it might be orbiting the sun, but not all comets orbit the sun. Some comets come in, and then they shoot off, and they never come back again. So there's a distinction we want to be able to make. Okay, so our goal is to find the path of that object. R satisfying this inverse square law, where K is M, M, G, N. Okay, so I said, just to repeat, this is an approximation of the reality in various ways, but in particular that really there's an orbit that this object is doing due to the gravity of that one, but it's much, much, much smaller than the orbit that that one's doing. So we're going to fix that one as our origin and just focus on the motion of that one. It's called the Kepler problem. So in early 17th century, Johann Kepler devised 3 scientific laws about the properties of planetary orbits. The fascinating thing was this was before Newton even had done calculus. So he was really just examining data that other people had collected and processing that data to come up with these laws. Our goal is to reproduce these same laws, but within the framework of solving these equations. Okay? And we'll list those laws that Kepler found a bit later. Right, so if I define this just for notation as, say, capital F of R, that's our central force. So right away, we can conclude, based on things we've said in previous lectures, that this angular momentum about the object at M, the origin, r cross M r dot, is constant. And that further implies that the motion is planar, as we've seen before. Which means that we can work in what we might as well call the xy plane, but we'll really do this in polar coordinates. Okay. So let's start with Newton's second law. So N2 with R equals R E R. We've already done this exercise a few times. So I get M R dot dot is M R little scalar R dot dot minus R theta dot squared E R plus 1 over R d dt R squared theta dot E theta. Same formula we've seen a few times. Equals S, let's write it as F of R ER. And some of our same tricks are going to work. There's no E theta component to the force, which means that this thing is not balanced by anything, which means that that d dt is 0, which means that r squared theta dot is constant, which is what we've been calling h, is going to apply as usual. So the E theta component, we get r squared theta dot equals h is a constant. Let's label that as kind of fact 1 or equation 1. And if we look at the ER component, things are a bit less nice. We have M R dot dot minus R theta dot squared, which I can write as M R dot dot minus, same trick. I don't like the theta dot there, so I'm going to view that as an R theta dot squared, but then I get an extra, I get too many R's, so I have to divide by an R cubed. So that's H squared over R cubed equals F of R. And that's, they call that equation 2. Okay. So, in principle, I could try to solve that equation. That's a second order equation for R of t, right? It's not a nice one. It's got a 1 over R cubed here. It's got a 1 over R squared over there. This is very nonlinear. I don't know any methods to solve that exactly. And indeed, once I solve it, I still then need to work out theta of t, right, which I could get from here. So if I knew R of t, I could stick it in there, and then I could solve this equation for theta of t, and now I've got the path R and theta of t. But that's very hard. So we need a trick. Before we get to a trick, let's take the simplest case. The simple case is where theta dot is 0. So if h is 0, and when does the simple case hold? The simple case holds if theta dot is 0 at t equals 0. So I have an object far from the sun, and I just let it go from stationary position. It's going to have no angular component. It's just going to go straight towards the sun. That's going to be a radial path, right? So theta dot is 0 and h is 0, then we get a radial path. In other words, this equation becomes a lot easier. It just says r dot dot is f of r. And that's called a radial Kepler trajectory. I'll say that's not trivial, because the f of r still has the nonlinearity, the 1 over r squared. So you still have to figure out how to solve this, but that is a solvable equation. I think I put that in a problem sheet, so you work out those paths. Okay. But that only works in the case where the theta dot is 0 and the trajectory is very simple. Right? So that's the less interesting one. If h is non-zero, we need a trick, and here's the trick. A trick is I'm going to define u as the variable 1 over r. And what we'll see is, in terms of u, so I'm going to do two things. I'm going to define u as the inverse of r, and my idea is to eliminate t, make t sort of a hidden variable, and solve for the path as a curve u of theta. So eliminate the independent variable and see if I can get an equation for u of theta. Okay. I think we have just about enough time to see how this trick works, so it's just being careful about how I convert into the u via chain rule. So r is 1 over u, which means that dr dt is negative 1 over u squared du dt. Now I'm going to write that as negative 1 over u squared du d theta dt. But I know that r squared theta dot, which is r squared d theta dt, is h. So therefore, dr dt has a d theta dt, which is an h over r squared, but r squared, 1 over r squared is u squared. So that means that dr dt, d theta dt, I can write as h u squared. And therefore the u squared and the u squared cancel, and I get this nice expression that dr dt is just minus h du d theta. With me? Now we need to go second derivative. Second derivative, r dot dot. That's d dt of dr dt. And as we've just worked out, when I take a d dt, I pick up this d theta dt factor. So I'm going to write d dt as d theta dt. And dr dt we've just written as minus h du d theta. But this is nice because I'm taking a d theta, h is constant, so there's just like a second derivative of u with respect to theta, and then I've got this d theta dt, which as before is hu squared. So therefore, r dot dot becomes, I have an h there, I have an h that I can pull out there, so that's minus h squared u squared d squared u d theta squared. So therefore, let's see what Newton's second equation, well not that one, this one, look at the ER component there. 2 becomes, this is where all the magic works. Put all these things together, you get a minus h, so there's an m, minus h squared u squared d squared u d theta squared, r dot dot, minus h squared over r cubed, but that's just like a u cubed, so that's minus h squared u cubed, equals f, but f is really k minus k over r squared, so that's minus k u squared. And that's lovely because I can cancel out a u squared from everything, and I'm left with a very manageable equation, m d squared u d theta squared plus, I'm going to put the h on the other side, cancel out a minus everywhere, so I get plus u, actually let's get rid of that as well, plus u equals k over h squared. Sorry? Yes, sorry. I was going to cancel the mass out of the k, but we'll do that. So the mass there. Okay, we'll pick up with this next time, but as you can see, this is magic because that's a second order, that has solutions of sines and cosines, that thing's just a constant, and then we need to put the pieces together to see what the possibilities are. Good, let's stop there. See you next time.